Hello and welcome to my presentation of the ETCR infrastructure and datasets. My name is Robert Heumüller and I'm a researcher and PhD student at Otto von Guericke University in Magdeburg. To my right, you can see my co-authors Sebastian Nielebock and Frank Ortmeier, who's also my supervisor. Together, we created ETCR to give the automated software engineering community access to standardized datasets for research on deep learning with regard to modern code review applications. In particular, we would like to support creation of models that are capable of automating or partially automating specific code review activities.
Let's take a look at some very recent examples to get an idea of where this kind of research is headed. The first group of researchers used neural machine translation algorithms to learn method-level code changes. In their earlier research, they only used the source code revisions from before and after a code review happened, whereas in their recent research, which is going to be presented shortly at ICSE, they also used the review comments themselves. For the second example, deep review sharing, the researchers developed a new type of learning-based code clone detection and used that to find code clones across multiple projects. They then used these code clones as anchors in order to transfer reviews which were present in one project onto similar code in another project where there were no such reviews available. What those two approaches have in common is that they operate at a rather coarse level of granularity, and this is where our own research comes into play. Our goal is to learn a more fine-grained mapping between source code and code review comments. For this, we want to use graph learning on program representation graphs. So if we look at an example on the left, there's a typical review comment regarding a constant which is not given a proper name, and the job is now to identify the relevant AST substructure, in this case the assignment statement, and the nodes below to which the comment applies. Given enough of these tuples as training data, we believe it should then be possible to train an AI to classify graph substructures using the topics learned from the data. We created the ETCR infrastructure because we found that none of the existing code review datasets was likely to be sufficient in terms of quantity and also in terms of the contained data for learning the fine-grained mapping between code review comments and AST substructures. For these envisioned learning tasks, it is essential to have the full reviews available as well as the full source code of all commented revisions. We checked all the existing review datasets we could find for these criteria, and it turned out that all of them were lacking in some aspect. For example, that they didn't have the line information contained or that they only had abstracted versions of the source code. Of all of the existing code review datasets, the code review open platform, in short CROP, was the most promising. However, CROP relies on the Garrett code review system as its source of data, and Garrett is known to rewrite project histories, which makes it very difficult to come up with the full revisions of source code at the time of the code reviews. Work around this problem, CROP only uses very specific Garrett projects which keep a mirror of their entire development history, which they use as a source for the revisions they include in the dataset. That's the first reason why we decided to use GitHub pull requests as our source of data for ETCR. The second reason is that GitHub offers thousands and thousands of potential projects which make ETCR very extensible. Using our tooling, it is only a matter of a little bit of configuration to create additional datasets if desired. When comparing the ETCR Elasticsearch dataset to CROP, for example, in terms of the raw number of comments, CROP is still larger. However, this is not really an issue, as the ETCR process can be applied to basically any GitHub project to create much more data if necessary. If you are interested in further details about the comparison between ETCR and the other datasets, please consult the paper. We will next dive into the concrete Elasticsearch dataset to give an explanation of our relational data model before concluding with a tutorial on how to use the provided infrastructure to first mine a new dataset from an arbitrary GitHub project, and then how to use the utilities that we provide in order to easily find the links between a code review comment and the associated AST nodes. All ETCR datasets are stored in PostgreSQL databases. So the ETCR Elasticsearch artifact mainly consists of a large Postgres dump, and the README you see here is shipped with the artifact, and it contains instructions on how to restore the dataset into your PostgreSQL installation. Here you see an overview of ETCR's relational data model. We won't go into detail about all of the contained fields, but rather give an overview of the most important aspects. First, we have a table which stores the metadata of all the pull requests in a project. To each pull request, developers can add a number of new revisions in the form of the commits. And then there is an iterative process of commenting and once more creating new revisions. For each comment, we not only store the message and the author, but also the data which is required to identify the relevant lines in the corresponding code change. In GitHub, it is also possible to create comments directly on the pull request, which are not associated with some particular change in source code. So therefore, the relationship between the comment and the pull request is mandatory, whereas the relationship between comment and commit is optional. Next, we download the content of all the relevant source files and the revisions that were commented. We store both the path to the file and the content they had at that point in time. Finally, we use the Java lang parser to create ASTs for all Java 8 source files. We store ASTs both at a file level and at an individual method level. The method level ASTs are distinguished by their parent AST and line range properties. The parent AST reference resolves to the respective file level AST that contains this method, and the line start and line end fields indicate the line numbers of the first and last tokens in the respective AST. These are convenient for identifying the correct method ASTs based on the line ranges and review comments. The payload fields AST string and AST pickle contain a string serialization of the AST and also a binary serialization, which can be restored using Python's pickle module. Next, we look at an example of how we find the correct source code revision for a particular comment. For convenience, we will use the simplified comment view instead of the bare comment table, because this removes one layer of indirection. As you can see, all author names in this table and also in the other tables have been masked for data privacy by using SHA hashes. Now let's find a suitable comment. For this purpose, we tell the IDE to only show Java source files. Then we select a desired comment. Let's take this one here, and we can look up the value of the Git file reference over here. As there is no original start line defined, we know that this is a single line comment on line 38. We take note of the Git file reference, and then we open the Git file table to retrieve that file. Here we can see the original file path. It's the result utils class. And here we have the file content. And here on line 38, wherever that would have been, we had the original comment we were looking for. As a starting point for the further exploration of the dataset, our artifact also includes an SQL script with lots of queries for all the statistics that we showed in the paper. This concludes our overview of the ETCR data model and the ETCR Elasticsearch dataset. If you are interested in finding out how to actually create a new dataset using ETCR, please see our second screencast, which features a tutorial on this subject. Thank you for your attention.